Hello and welcome to Measurements with the Gamma Scout in a nutshell. After having gained insight how the Gamma Scout's GM tube works and how we can use it for counting measurements, let us have a look into measuring the typical types of radiation with the Gamma Scout. In this video, we'll show you the measurement of alpha particles. Alpha radiation can be originating from different sources. Uranium and thorium, two of the most widely abundant radioactive elements, emit alpha particles. Both can be found in numerous ores and minerals in Earth's crust. They may also be present in trace amounts in widespread rock types, such as granite. In many countries around the world, there are regions with elevated levels of these elements. The decay of naturally occurring uranium and thorium gives rise to various decay products, forming so-called decay chains. This means that the decay products of uranium and thorium are radioactive themselves. These decay chains may have several members before they end in stable isotopes of lead. One important member of the uranium decay chain is the radioactive noble gas radon. This noble gas has received much attention as it can carry a high risk for lung cancers. Elevated radon levels in workplaces and homes need to be identified and mitigated, for example by assuring adequate air circulation and structural sealing against the subsoil of buildings. Alpha radiation is the most challenging type of radiation to detect in everyday life. This difficulty arises from the fact that alpha radiation, as highly ionizing radiation, can be shielded easily and effectively. To demonstrate this, we have set up a small experiment. On an optical bench, we have placed an alpha-emitting source in front of our Gamma Scout. The lever is set to the alpha, beta, gamma position. In other words, there is no shielding in front of our GM tube, so we can see the end window. Let us recall, the Gamma Scout averages the current count rate over 2-second intervals, which may lead to temporary fluctuation in the measured values. Beforehand, we assessed the count rate without a source, again without shielding in front of our Gamma Scout. This reading reflects the ambient radiation, and in our measurement ranged from 0 to 0.75 pulses per second, commonly referred to as the background. We observe that at a distance of 10 centimeters in front of the source, the measured count rate is equal to that of the natural background radiation. We will now decrease the distance to the Gamma Scout. Even at a 5 centimeters distance, we still observe no notable increase in count rate. Only when the source is positioned directly in front of the Gamma Scout, it registers a substantial rise in the count rate. Now let us change the measurement window to beta and gamma by turning the lever. This places a thin piece of aluminium in front of the tube. Notice how the count rate promptly decreases to the value of the previously established background count. Hence, we observe that the alpha radiation can be effectively blocked by just a few millimeters of low-density matter. It is worth noting that even a simple sheet of paper is adequate to shield against the entire alpha radiation emitted by our source. Due to this fact, the measurement of alpha radiation proves challenging in practical scenarios. Our point source, specifically manufactured for calibration measurements, shows minimal self-absorption. In contrast, real samples present a distinctly different scenario. When searching for natural radionuclides like uranium or thorium outdoors, they are seldom found in pure form. Typically, they are embedded in rock formations, leading to considerable self-absorption. Achieving noticeably high readings on the measuring device due to alpha radiation, such as from a sample of uranium or thorium mineral, is uncommon in the majority of cases. The impulses directed from natural samples usually originate from the beta and gamma emission of nuclides within the decay chains. Hence, it's much more favorable to measure such materials in the beta-gamma mode. In this context, some alert users have asked us the following question. How is it possible that my Gamma Scout displays the same readings with and without shielding, even though there has been a radon measurement with another device that determined an elevated concentration? Direct measurement of indoor radon, based on its alpha emissions, proves to be quite challenging. We'll try to elaborate on this. The radon activity in a room is measured in becquerels per cubic meter. In Germany, where we are located, national radiation protection legislation recommends an average annual indoor radon activity of 50 becquerels per cubic meter. In other words, 50 decays per second within an air volume contained in a cube of 1 meter in length in each direction. Let us generously assume that the gamma scout would detect all alpha particles within a cubic air volume with edges of 10 centimeters in front of the tube. This air volume precisely equals 1 liter of volume. As there are 50 decays in a volume of 1 cubic meter, which equals 1000 liters, we have 50 decays per 1000 liters per second. In 1 liter, there are 1,000th of 50 decays per second, which is 0.05 decays per second, or 1 decay in 20 seconds on average. If we assume a more realistic counting efficiency of 5%, we would record 0.0025 counts per second. If you remember that the background is fluctuating between 0 and 1 pulse per second, it becomes apparent that this value is indistinguishable from the background, even with extended measurement times. In this example, it does not matter so much in which position the front lever is placed. The significant contributors to the count rate, and consequently the reported dose rate, are gamma emissions from terrestrial sources, or the measured cosmic radiation. For professional measurements of indoor radon concentrations, as done for example by authorities, specialized equipment is used. These devices are notably more intricate and consequently significantly more expensive compared to the Gamma Scout. And on that note, we bid farewell and sincerely thank you for watching. If you've enjoyed this video, please give it a thumbs up and subscribe to our channel to stay tuned for all our future content. If you have any questions or suggestions, feel free to leave a comment below. We look forward to seeing you again next time. Until then, take care and see you soon.